Hello and welcome to a video about Case Study 1. Case Study 1 is a part of the testingcomplexsystems.com website. The case study introduces a data handling component called GDS. The Global Data Store, or GDS, is a lightweight data handling component. It works well in test platforms. We're going to be reviewing GDS features using a toy application. Let's go and get the code. Here's how to get the code from GitHub. First, we clone the code to the local system, cd to the directory, take a look at the subdirectories in that directory, cd to the case study 1 directory, and take a look at what's in there, 2 files. The dd file is a schema file. It's processed by a code generator to produce Python code. The other file in green is the Python application executable, which uses the above generated file. Let's start by looking at the .dd file, which contains the schema. The schema file starts by defining 3 tables: a county table, a farm table, and an animal table. Each table has columns and, if necessary, an index. There are naming conventions in force. They're few and pretty easy to spot. One thing that is not a convention is the leading G on the table names. That's a personal preference of mine. Each table requires a name and a row status column. 2 tables have references to other tables, rows and other tables. The farm table here has a reference to the counties, and the animal table has a reference to the farms. When an index is used, like here in the county table, it keeps the specified column unique when it's used at runtime. 2 required columns are the name column and the row status column. You'll see how the name column is used here, and the row status column will be talked about in case study 2. First, let's run the code generator on the schema file and review the generated .py file. We go over to the terminal window, hit the command with enter, and get output that's saying it successfully wrote the .py file, and a reminder to use the row status file, which we will get to in case study 2. Let's take a look at the resulting code. The 3 tables are defined in these lines in the .py file. You can see lists and dictionaries that are global shared. After the global variables are defined, the file goes on to define some add a row routines, one for each of the tables. Here's one for the county table. Here's one for the farm table. Next, we generate delete row routines for each of the 3 tables. And next, we define 3 dump row routines, one for each of the tables. Let's now look at the application code. It starts out by consuming the .py file, but not before it checks to make sure the py file is not out of date. It goes on to define a single lock with a lock object and unlock object routine. It goes on to define a routine called add one animal, and we will use that further down. The main part of the code starts out by defining 2 counties, County A and County B. We use the add a row routines, and we specify the names of each of the counties. Then we define 3 farms and assign the farms to the counties, the first to county A, the second to county B, and the third to county B. County and farm tables are set up. We go on to add rows to the animal table. Here we're spawning processes and threads, and each of those spawned processes or threads executes the add one animal function defined above. Let's go back to the add one animal routine and take a look at it. 3 lines of code are critical: a lock, an add a row call for the animal table, and an unlock. This routine is executed by 39 processes or threads at the same time. Only the calls to lock and unlock keep the data in the tables organized and correct. Once the processes and threads complete, we dump the county, farm, and animal rows. We then print out a small report. Here are chickens in County B. Here's the code to do that. It can be done a number of different ways. And we finally sort and print out the data. The final piece of code loops on input from the user. The user puts on an animal reference value, and then the animal associated with that number gets printed out. A farm associated with the animal gets printed out. The county associated with the farm gets printed out. Each of these references are what are called cascading references. Now let's run the code we were just looking at. We start out by adding the 2 counties and 3 farms. Next, we add animal rows randomly. 9 processes, 30 threads, 39 activities total. Each one adds an animal. Here we dump the counties, the farms. Stop and take a look. Here's a farm. It's telling you what county it belongs to, and it has the farm name in here as well. To finish the dumping, we dump out the animal table, which has 39 rows in it. Next, we print out that small report of chickens in County B. And finally, we go through and dump out animals, farms, and counties associated with a given animal. Here we see animal table with 39 entries. We're looking at the entry with index 1. Here's the farm associated with that animal, farm B. This farm belongs in County B as well, and you can see that that is true down here. So the fundamental GDS features are to support relational tables as lists and dictionaries in shared memory. Note that no special Python syntax is needed to work with the data, and concurrency can be managed with system locks and row locks, which is described in case study 2.